Thank you for your trouble. She's like.
Already did all the parts.
Yeah. I need to do this, but I feel like that's some how, because, yeah, we. that it's supposed to. Do one of the parts. Then I was like, oh, what about? That was the one solved, the front right top. That's metric.
So.
Yeah, one how there's like one like a bush on, I didn't know, it was like a screw. The one has the top end of.
Oh,
Yeah, like. I don't. Get them. Well, I just wanted to clear it up before I started. I started, but then I'm like,
Yeah, Professor.
I feel like he.
Last lecture, we just did lecture night.
Yeah.
All right.
Yeah, today is the activity. Yeah, Tuesday was just a lecture.
Pretty much like. Yeah.
I thought that's. So, I don't know, I'm just gonna wait up on that. Assembly. And then.
Yeah. Just ask him on Saturday to see what he wants.
Instructions for the extra.
The extra, yeah.
I want a concrete, you know. Not up to the end.
Yeah, the whole story. Like, we slept it.
Mhm. Yes. They'll start on my materials. So on the 16th. And I want to start on this one. This is on the 19th. No. And I want to ask questions. Yeah. And then-
Got a lot of shit to do.
Yeah. And I tell my. Other than one important. Mhm. So, creative.
Oh, yeah, that's. You know, it's gonna be like social theory, so.
Yeah, you know.
Elements of pipelines. That's the way. We'll just matrices. It's matrices, matrices. I know, but I'm not doing it.
Oh, I love it. Oh, okay.
Then.
It's easy for people on that.
Mm.
All right, it's 5:30. Let's go and get started. Good evening, everyone. How's everyone doing today? Good to hear. All right, so today's our next ANSYS activity. I think this is the last activity that I'm going to grade. So I do have one more activity planned after this, but it's going to be during the last week, and so I know everyone's going to be focused on the final project, but so this will be the last project that I grade, but not the last activity that we. All right, so the subject for today is going to be modal and vibration analysis in ANSYS. So we talked about this on Tuesday as we introduced the idea and what it's about. And today we're actually going to see how this is done in ANSYS itself. Okay, there is going to be a little bit of added content for this activity. Nothing that you guys have to do, but I do want to show you guys how to do frequency response in ANSYS as well. So I do have a separate handout for it, but since we're going to be doing modal analysis, we might as well do frequency responses as well. Okay. All right, so you guys know the drill at this point. So if you haven't already, go ahead and start up ANSYS Workbench. The instructions for the activity and the CAD file for the activity are both available online. There is a little bit of a typo. I think I just forgot to change the date here, but the due date is actually Sunday, May 4th. So it's going to be on Star Wars Day next Sunday. So there is no Sunday, May 3rd. I think it was May 3rd, maybe last year. Okay. So I think I have to clear that up on Canvas as well. Yeah, so actually let me change that right now, just so it's due on May 4th. But yeah, you guys will have until next Sunday to get this done. Okay, any questions I can answer before we get started for today? Okay, all right, so let's go and get started. So if you haven't already, go ahead and open up Workbench. Okay. So actually, like I mentioned that if you're going to do modal analysis, there is an analysis system for that. So you can see here that there is a modal type of analysis here. Okay. So if you're just interested in modal analysis, you can do just that. But actually, I'm going to show you how to take a static structural simulation and link that to your modal analysis. Right? So let's start with static structural and drag it over here. Okay. Okay. And then let's import our geometry. So our geometry for this activity is going to be a gearbox. So go ahead and hit browse. We're going to load in our gearbox. Okay. So this geometry was actually created within ANSYS itself. And so, if you wanted to, you could do optimizations. Okay. So before we jump into ANSYS Mechanical, let's go ahead and change the material properties. Okay. So for this simulation, we're going to need two materials. And so we're going to need stainless steel, and we're going to need gray cast iron. Okay. Okay. So just like we've done, a few times already. So go ahead and click on, double click on engineering data here. Click on engineering data sources. Okay. So both of these materials should be under general materials. So you click on general materials here. You can see I have gray cast iron here. So let's go ahead and click on the plus sign next to gray cast iron. Okay. And let's also add stainless steel here as well. So I think stainless steel is actually quite similar to structural steel. But we'll go ahead and add that to the so, looking at the stats here, very similar, but we'll add stainless steel here. So you should have three materials in your project. So you should have stainless steel, gray cast iron, and the default structural steel. Okay. All right. All right. So once you are done adding material properties, let's go ahead and close out of this. Double click on model. So let's go ahead and open up our ANSYS Mechanical here. Okay. And we'll be adding our mesh and boundary conditions, just like we've always done. Okay. Now the reason we're starting with static structural is a couple of reasons. And so one reason being that like we mentioned on Tuesday, that when you're running a modal analysis and you're solving for the resonant frequencies, the state of stress within the material, does affect the resonant frequencies. And so we're starting with static structural so we can create, a situation with some static stresses. Okay. So we'll see how that affects our results for the resonant frequencies. But also later on, when we do frequency response, you'll be able to see kind of the result of resonance as well. So you'll be able to compare kind of the deformation that you get from a static simulation versus when resonance is occurring. And you'll see that resonance is going to act to amplify our static, our static deformations. Okay. Okay. So after you've loaded in your geometry, you should see the part right here. Okay. So our geometry today consists of three separate parts. And so we have the base plate, and so that's where we're going to fix it. We have the flange, which is where shafts and rods are going to attach to. So this is where we're going to apply our forces. And then we have the main structural housing here. Okay. Now, if you notice, the housing part here has a question mark next to it. And that's because, this housing component is actually defined as a shell. So it's a little bit hard to see because, the bottom of the part here is covered by the base. But this housing part actually is a shell element. So we actually do need to specify a thickness here. Okay, and so for the thickness for this part, we're going to specify a thickness of 3 millimeters. So if your unit system is not in millimeters, go ahead and change that up here. Okay. And so go ahead and specify a thickness of 3. And then that's going to change your the indicator next to housing to a green check. Okay. All right, so another thing that we're gonna need to add before we start to mesh is we need to add our contact regions here, okay? So right now there's only one contact region, and so that's in between the housing and the flanges, okay? But since our since our housing here is a shell, it's actually not properly attached to the base just yet. Okay, so let's go ahead and do that. So let's go ahead and add a contact region. So just like we did in activity 4, right click under contacts here and insert a manual contact region. Okay. And so we're going to use this to connect the housing or the gearbox to our base. Okay. Okay, so just like we did in ANSYS activity 4, we need to specify our 2 parts of the geometry here. Okay. We need to specify our target and our contact. And so remember, the difference between these is that the target has to be the bigger of the 2 surfaces, okay? And so since we're connecting the housing to the top of the base is given by this plane right here, this surface, okay? So we're going to specify that as our target. And then for the contact, we're going to specify the bottom edge of the housing here, okay? Now, and so you have to be a little bit careful here, so make sure that, if you want to be absolutely sure, you can change the selector mode to edge mode up here. Right? Right, and then hold Control and click on your keyboard and click all 4 edges around the bottom side of the house. Okay, so once you have those 4 selected, go ahead and click apply here. Okay. So that way we've connected the bottom of the housing to the top of the base. Okay, and so that's all the adjustments that you should have to do. So just to summarize, make sure you specify a thickness of 3 millimeters for the housing, and then for the contacts, make sure that you specify a bonded support between the bottom of the housing and the top of the base. Okay, any questions on this so far? Okay, good. All right, so next thing we're going to do is we're going to specify a mesh. Now for this activity here, we're not going to be too picky on the mesh, just because modal analysis is actually a pretty cheap, relatively cheap analysis. So what you're going to see is that the resonant frequencies that you get should converge pretty quickly. So I'm just going to specify a size, and so I'm not going to bother changing the method or anything here. So let's specify a mesh size of I don't know, let's say 8 millimeters. But you could probably even use the default mesh size and it should be fine as well. So let's see what this looks like with 8 millimeters. Okay. All right, so this is what my mesh looks like with 8 millimeters. And so you can see we have hexahedrons at the base. We have quadrilateral elements for the housing shell. And since the flange is a rounded geometry, you can see the ANSYS has chosen tetrahedral elements for that. Okay, but again, don't fuss over the mesh. Don't fuss over the mesh too much in this activity. You're going to get pretty consistent results even with a fairly coarse. Okay. All right. So let's talk about the boundary conditions next. Okay, so if we go to the activity here, if you scroll down enough, you'll see the loading conditions that we have. Okay, so we're going to be applying force loads on all 4 of these flange holes here. Okay, so you can see from the top view, I've labeled them A, B, C, and D. Okay. And the forces are given by the following here. So you can see we have forces in all 3 components in some cases. So X, Y, and Z. Okay. Okay, so you can go ahead and apply forces on these holes here, okay? But we're gonna apply forces in a little bit of a different way, okay? And the main reason I'm introducing this now is that, you know, some of you may be interested in doing this for your final projects, okay? So we're gonna be using a different type of load here known as a bearing. Okay, okay, so if you right click on static structural A5, you go to insert, okay? You'll see that there is an option for loading here called bearing load, all right? And so if you read the description for bearing load, you can see that it says it inserts a bearing load boundary condition that simulates the radial forces applied on the interior of a cylinder, okay? So this is a special type of load that you can apply on circular type geometries to simulate the fact that, you know, you may have a rod that's inserted into the hole and kind of pushing up on one side of the hole, okay? Now, why would you want to do this, right? So normally, you know, the way that we would do this is that we would just select a simple force load, okay? And then apply it to, you know, let's say the interior surface of this hole, okay? And then you apply your force and components. Right? And then you specify X, Y, and Z. So that's how we've always done it, right? Now, you know, I think I may have mentioned this before, but you know, when you specify a force that's going to be distributed over a surface like this, you know, what ANSYS actually does is that it evenly distributes that force across the entire surface. Okay. So let's say that we apply a force in the X direction. So let's say that we apply a force of, you know, I don't know, 5,000 newtons. Okay. So we have a force of 5,000 newton that's being applied in the X direction. What ANSYS is actually doing is that it's taking that 5,000 newtons and, you know, distributing it as if, you know, every single part of that surface is experiencing an equal amount of force. Okay. So that means, you know, this part of the surface is experiencing the same force as this part over here. Okay. It's evenly distributing it across that surface. Now, for a lot of cases, this is what we want, right? So for a lot of cases, you know, we do want our force to be evenly distributed across our surface, right? But for a cylindrical kind of hole like this is actually a case where we don't want that to occur, okay? Because if you can imagine, right? So if you can imagine, you know, a rod that's being inserted into this hole right here, and then there's a force being applied on this rod, right? Now, overall, there's going to be a net force that's going to be applied on this hole right here, but it's not going to be evenly distributed because the force that's being applied is due to the contact of that rod with the surface here. Okay. If you think about it, you know, if you put a rod in and you pull it one way, right, most of the force is going to occur on the portions where the rod contacts the inside surface of that hole. Okay. So what you have here in this case is kind of an uneven distribution of the load, right? That actually looks something like this. Okay. And so, you know, this kind of has a similar situation where you have a hole here in a rod that's being inserted, and we have an overall net force being applied upwards. Okay. Now, because that force is being applied by a rod, you know, most of that force is going to be concentrated on the upper half of that hole there, right? Because it's due to that rod contacting with that inner surface, right? And so we want to simulate that. So we want to, you know, make our loading conditions a little bit more realistic, okay? And so the way that we can do that is, you know, not by applying a force load, but by applying a bearing load instead. Okay, so if we apply a bearing load, so let's say that we apply a bearing load on this surface here, okay? Okay. And so once again, we can define by its components, okay? And now you can insert a bearing load, so let's see, that's hole C, okay? So hole C has a force of 3,000 newtons in the X direction and minus 30,000 newtons in the Y direction. Okay, so let's go ahead and put that in. 3,000 for X, minus 3,000 for Y. Or minus 30,000, excuse me. So you can see that puts a force, you know, mostly in the Y direction, but a little bit X as well, okay? But now that force, or you know, how that force is distributed is a little bit more realistic to, you know, how that force would be applied in practice. Okay. Okay. All right, so go ahead and do that. So I'll give you guys a few minutes to work on that. So we have 4 different holes here and 4 different loads. Okay, so go ahead and apply those loads and make sure to use the bearing loads on those holes. Okay. Now you may run into an issue with holes A and D, but we'll talk about that in a second. So go ahead and apply your 4 bearing loads. I'm going to go ahead and apply it on my end too. And if you have questions on this part, just go ahead and raise your hand. I'll make note. Don't forget that you can relabel your loads, so you can rename them. And so in this case, it's probably useful just because there's so many loads to apply here. How's everyone doing applying these loads? Anyone run into any issues yet? Okay. So if you try to apply all of the loads in the bearing loads, you might have run into an issue with load A and D. Okay. Now holes A and D here, they're unique in the sense that they actually have a load in the Z direction. Okay? Now, if you look at the Z direction actually goes right down the barrel or right down kind of the axial direction of the holes themselves. Okay. So a limitation of the bearing load is that you can only apply loads in directions that are perpendicular to the cylinder wall. Okay. And so in this case, because the cylinder walls are, in the XY plane, right? you can only apply loads in the XY direction. So if you want to apply a load that actually goes down the length of the hole, you actually need to apply that as a separate load. And so, so for hole A and hole D, you know, when you apply those Z direction loads, you actually need to apply them as a separate force condition. Okay, so you can't actually apply them as a bearing. Okay, so just be careful of that. So bearing loads are really, you know, are really nice. They're kind of a nice feature within ANSYS, especially if your geometry has a lot of holes and you're applying loads inside those holes. But just be aware of the limitations as well. And you can't apply any axial forces or axial loads on those, you know, on those parts of the geometry. All right. Any questions on that? Okay. All right. And so if you're done applying your loads, go ahead and add in the total deformation and the equivalent stress. Let's go ahead and hit solve. Okay. Oops, I forgot. Don't forget your fixed constraint. You need that as well. Rookie mistake. All right, so add your fixed support. So our fixed support is going to be on the bottom of the gearbox. There we go. All right, so now we're ready. So now we are running our simulation. Okay, and so you should get a total deformation that looks something like this. And then your equivalent stress probably going to look something like this. Okay.
The axial load is normal load on the face, right?
Wait a second.
The axial load is just a normal load.
It's just normal force. Yeah.
On the face, right? Same
Yes.
face.
Yeah. Same face. Okay. All right. So this is what we have here. And so I'm looking at kind of the comparison with the activity. So I am using a little bit of a finer mesh here, and so that actually, you know, makes our deformation computations a little bit more accurate. Okay. So don't be alarmed if your deformation is not exactly what it is, you know, in the activity. You know, it does actually depend strongly on your mesh density. So probably what I should have done for this activity is I should have done a mesh convergence test. You know, but we'll just kind of roll with what we have. But you should get a deformation field that looks something like this. So most of the load is going to be applied on load D, and so or hole D, and so that's why this is kind of pushing down. Okay. And a lot of your stress is going to be occurring right at that kind of intersection in between. Okay, so that's just kind of very kind of basic static structural analysis for this part. Any questions on this so far? Okay. All right, so that's our setup here. So let's go ahead and move on to the new stuff. So let's go ahead and close out of ANSYS mechanical here, so that we can start to do our modal analysis. Okay. Okay, so let's go ahead and go back to ANSYS workbench here. Okay. And what we're going to add here is we're going to add a modal analysis to this. So go ahead and click and drag modal. Okay. And you're going to drop modal on top of model in workbench right here, just like this. Okay. And so what this is going to do is that this is going to link, it's going to link together your static analysis. And so it's going to inherit the mesh, the boundary conditions from your static analysis, and use that as the basis for your modal analysis. Okay. Okay, so I'm going to go ahead and click and drag that. And what I'm going to click from here is setup. Okay, so after you've connected your modal analysis to your static structural, go ahead and double click on setup to reopen ANSYS mechanical, except now it's going to have the modal analysis attached to it. Okay. Okay. All right, so was everyone able to kind of get to this point here? Everyone have modal opened up on ANSYS? Okay. Okay, and so from here, it's pretty straightforward. So remember, all that we're interested in the modal analysis is going to be our resonant frequencies. Okay. Now, there's two ways that you can do this, and so one way that you can do this is you can do it without any pre-stress, okay? And so if you go under modal B5 here, you'll see that there's a setting for pre-stress, okay? Right now it's set to none, but if you want, you can set the pre-stress environment to static structural, which it seemed to do kind of automatically for me here. Okay, so actually let's start with that. So let's change our pre-stress settings to static structural, right? Right. And then let's go ahead and hit solve. Okay, so what ANSYS is doing is basically taking the result of your static structural analysis and then using that as the pre-stress together with the geometry and the material properties. And then that's going to compute our resonant frequencies for us. Oh, you know what? I forgot to do something. So I forgot to change the materials of our gearbox. So that's probably why our deformation is quite a bit different than outside. So let me change that. So I'm going to change the material, but let's look and see what the resonant frequencies are, just so that you can kind of see from here. Okay. Okay. And so with, because right now the entire structure here is made of structural steel. Okay. And so just by clicking solve under your modal analysis, okay, and if you click on solution B6 right here, you can see in the bottom right hand corner you'll be able to view your 6 resonant frequencies. Okay. So the first resonant frequency here is 344.89 hertz. Okay, so that's the first time that resonance is going to occur when you achieve a oscillatory load in that ballpark there. Okay. The next resonant frequency is 605.79. The next resonant frequency is 623, then 674, 681, and 795. Okay. But just like we mentioned on Tuesday, usually most of the time you're going to be mostly concerned with the lowest resonant frequency, just because that's the one that usually causes the most damages as well. Okay. Okay. So let's go back and let's change the materials here. Okay. Okay. So let me just double check what materials we're using for everything. Okay. All right. So for the housing material. Okay, so for this part here, we're going to set this material to be stainless steel. Okay, so go back up to geometry, click on housing, and your material assignment is going to be stainless steel. Now for your other two parts here, your other two parts are going to be made of gray cast iron. So go ahead and choose that. And so for the flange here, go ahead and choose gray cast iron for that. And then for the base, go ahead and choose gray cast iron for that as well. Okay. All right, so now that we've updated our materials, let's go ahead and hit solve. So that's going to resolve everything for us. And so it's going to solve for the static structural analysis as well as the modal analysis. All right, so it might take a bit of time because it has to solve kind of 2 simulations at once. Right. Okay, so that's a bit better. So that's a bit more consistent with what's in the activity. So in the activity paper, then we have a total deformation of about 7.73 millimeters, and then our maximum equivalent stress is about 240 megapascal. Okay. Now let's see how that affects our resonant frequencies. So you can see our resonant frequencies have changed a bit. Maybe the first resonant frequency didn't change all that much, but all the subsequent frequencies change. Okay. Now our second resonant frequency is 503. Our third resonant frequency is 540. And 579, 671, and 767. Okay. All right, and so that's about it. And so that's modal analysis for you guys. And so modal analysis, the main thing that we're looking for are these resonant frequencies. And remember, you're going to be using these resonant frequencies to design your system. So for instance, this is a gearbox that's meant to go on a car, right? And so you want to make sure that these resonant frequencies, don't match the RPM of the engine that's attached to your car, right? Because that engine is going to be constantly applying this oscillatory load. And so you want to make sure that, your gearbox's resonant frequency is nowhere near what the RPM of that engine is going to be. Okay. Okay, let me show you one other cool thing you can do here. Okay. Now, in addition to the resonant frequencies, you might also be interested in seeing what the mode shapes look like as well. Okay. So to view the mode shapes, you're going to go ahead and highlight all 6 of these frequencies here. Okay. You're going to right click. And then after right clicking, you're going to click on the second option here for create mode shape results. Okay. Okay, so doing so is going to create 6 deformation plots here. Okay. And so to evaluate them, you can go ahead and click solve. Or if you want to do it just quickly, just go ahead and right click on solution V6 and then evaluate all results. That's a little bit faster, if you're just adding some additional results there. Okay. So now what you can see here is that, you can see how the mode shape is going to be if resonance were to occur in this, in this geometry. Okay. And so you can see here that, most of the resonance is going to occur in this top portion right here. Okay. In fact, you can actually play the animation to see what it would look like. So you can see that the entire structure is going to be kind of rotating to the left and right. And then this top portion here is going to be bulking out. So that's where most of the resonance is going to occur. Okay. Now be careful with this. And so remember I mentioned on Tuesday that when you're showing the mode shapes in ANSYS, ANSYS is going to present it to you in kind of a way that's a little bit misleading. Okay. Now, if you look at this mode shape result, you can see that it's listed as total deformation, right? And it even has units. And so from this here, it says that, the deformation is going to be 11.1 millimeters. Okay. Remember that when you're showing the mode shape results, that these are not true deformations, right? So this is not the actual deformation in this case. These numbers here are only there to show you the relative amount of deformation for that part of the geometry. Okay. We haven't actually applied any loads here, even though we did apply the pre-stress. So when you're showing the mode shapes, these are not true deformations, right? And so I put it in big serial killer writing. So just to emphasize it, not true deformation. Okay. So don't show me these mode shape results and say that this is the amount that is going to deform. That's not true, right? So these mode shape results, these deformation plots, quote unquote, are only there to show you just the shape of how the resonance will occur, right? And because if you look at the second mode, so if we look at the second mode here, we can see that the mode is completely different, right? And so if we play the animation here, right, you can see that this resonant mode here has to do with expansion of the entire material. It's not a left to right motion. Okay, but again, these magnitudes here, or these numbers, are not true deformations. So they're only there to show you just the relative shape. Okay. Any questions on this? Okay. All right, so let me show you just the rest of the activity here. So we've basically gone through problem 2 on the activity here. Okay. So problems 3, 4, 5, I'm basically going to ask you to modify certain parts of this geometry here to kind of see what effect that has on the resonant frequencies. Okay. So first one here is pretty simple. So first one for problem 3, I want you to change the material properties. Okay, and see how that affects the resonant frequencies. And so I want you to choose one material that's stiffer than stainless steel, and another material that is less stiff or more flexible than stainless steel, And you can tell the stiffness just based on the value of the Young's modulus. And tell me the results. Okay, so show me the resonant frequencies and show me the motions. Okay. So problem 4, I want you to change the geometry. So you can go into, since this part was actually made and designed in I believe it was Design Modeler, you can actually go in and adjust the geometry and see how that changes things. Okay. Or the easiest way to do this is that you can just simply change the thickness. Okay. So remember that earlier we changed the thickness of the shell element to 3 millimeters. And so you can change this to 4 and 2 millimeters and see how that affects your results. Okay. Okay. And so after you've made changes to the material properties and the geometry, in problem 5, I want you to design this gearbox for vibration. Okay. And so there's a target frequency that I want you to hit. Okay. So I want you to adjust the design of this gearbox so that you hit a natural frequency of around 200 hertz. Okay. Now, this might be difficult to get exactly on the nose, and so just like we've done in the past, as long as you're close, and so as long as you're within, maybe 10%, so 180 to 220 hertz, that's going to be good enough for me. Okay. But I want you to make changes, either to the material properties or the geometry or both, until your natural frequency is around 200 hertz. Okay. And then problem 6 is just summarize your findings. Okay. All right. Any questions on that? Okay. All right. So that's activity 7. So I do want to show you guys frequency response, but I do want to take some time right now to kind of walk around and see how you guys are doing. If you have questions on the activity, if you have questions on your project, I'll go ahead and answer those. And then probably at 6:30, maybe kind of the last thing that we'll do today, I'll show you guys how to do frequency response. So that's handout A6 on the Canvas site. Okay. But for now, I'll let you guys work. I'll let you guys work on the activity. And if you have questions, I think just raise your hand and I'll come up.
Yeah. That's somewhere. It's all.
Oh, you need to add a fixed support. Okay, so the fixed support has to go here. So actually what it's trying to solve for first is the static structural. Oh, oh yeah. Let me see what the. This one here. Yeah. Yeah, because when you specify a setting, you have to specify the part of the geometry. See, yeah, it might take a little bit of time because it has to solve for the static structural first.
The total definition for base is like showing up to the construction. Or 76.
Yeah, to me,
Where's the color geometry?
I've actually never seen the material.
A contender, I have
this
to-
this part here. But theory, it should be the same. Here. Recast iron.
It was.
It's usually when they apply the control.
Well, that's interesting. Like, you can do. You can do like hashtag these.
Well, we'll see what happens on that.
Also vibrations too. But it's,
Yeah.
it's a geometry. No, it's easier. Better one. Don't say this.
Now.
Make sure the geometry is like they're from. Like. When you get the connect. It's not.
Okay, looks like this has been updated. Yeah, I think it was the material. So it's pretty close. Not exactly, but this measures them all, of course, so it's gonna be a little bit different. Yeah, I think it was the, because I think same mistake that I had about. Okay, so I think, it took that long to solve this extra, so right now it's solved. I don't know if this computer might just be slow. But yeah, so once this finishes up, you'll see the reds pretty easy. Should be in the same ballparks. Yep.
that's what I want to understand. But how to so stress free is I don't think with this the big support.
Exactly.
Okay, and then this one is the burden.
Exactly,
Okay,
yeah.
thank you. Yeah, it's, yeah. Yeah. So, keep that.
All right, so one last thing I did want to show you guys before you guys head out for today is how to do harmonic response. So, you know, all we've done so far in modal analysis is just, you know, find out the resonant frequencies. But a lot of times, you know, when you are doing, you know, frequency response or resonance analysis, you want to actually see how much the deformations and stresses are going to amplify as a result of, you know, applying or achieving resonance. Okay. Okay, so let me just show you that really quick. And so if you're curious, you know, there is a handout for this online. So this is not part of the activity. So this is not something you have to turn in. But if you go under the lecture notes on the Canvas site, you'll see that there is a handout A6. So A6 is about harmonic response analysis. So it's a short handout, so it's only about 6 pages. But it kind of shows you kind of how to take a modal analysis and go to a harmonic response from there. Okay. Okay, so I'm just going to show you that really quickly so you can just kind of just watch and kind of see. Okay. So the starting point for harmonic response is always a modal analysis. Okay. So I'm going to click and drag harmonic response. And you're going to drag that on top of the modal analysis here. Okay. And so what that's going to do, that's going to link your modal analysis to harmonic response. Okay. And then from there, you should be able to double click on setup to reopen up ANSYS mechanical. So I know we've closed mechanical and opened it up again several times today. But each time we're kind of adding a new feature. So each time you add a new feature, you have to reopen up ANSYS mechanical. Okay, so I've actually never done this before. So I've never linked it from static structural to modal to harmonic response. So hopefully it inherits all the loading as well. We'll see. Otherwise, we're going to have to apply that loading ourselves. Okay. Good. Okay, so after you've loaded up your harmonic response, you can see here that we've created another analysis area called harmonic response C5. Okay. Okay, so just like we did from before, right underneath harmonic response, you're going to click under modal environment, and you're going to click on modal. Okay, so that's going to load in all the settings from your modal analysis. Okay. Okay, so with that should load in all the settings, the boundary conditions, the constraint, all that from your modal analysis. Okay. So the next thing you're going to click here is analysis settings, okay? And here we're going to be able to set various settings for our harmonic response, okay? So what ANSYS is going to do with the harmonic response is that it's going to take your loadings and oscillate them, with certain frequencies, okay? Now you have to specify how much frequency that you want to specify or what range of frequencies that you want to test in your harmonic response, okay? So the default minimum is going to be 0. But you have to specify a maximum as well. So let's specify a maximum. Let's specify a maximum of 600. Okay. So that'll test all the frequencies between 0 and 600. Okay. Okay. A couple other settings that we're going to change just to make things a little bit smoother for our results. So the next thing we're going to change here is cluster results. We're going to change this from no to yes. Okay. And the other thing that we're going to change here is we're going to add a little bit of damping just to make sure that our deformations just don't get out of control. Because normally when you achieve resonance and there's no damping in the system, the deformation just kind of blows up like to infinity. So we don't want that. And so we're going to add a damping ratio here of 0.1. Okay, so that's under damping controls, and all these are under analysis settings for the harmonic response. Okay. Okay. All right, so next thing we're going to add here is we are going to add in our solution here. So right click on solution C5, okay? And then from here, you're going to go under frequency response. And let's look at the deformation. That's kind of the easiest one to look at. Okay. All right, and so for the geometry here, we need to specify what part of our geometry that we want to view the frequency response for. So let's just view kind of the whole geometry. Actually, let's look at the flange. Okay, and then for the spatial resolution here, let's change that to maximum. Okay, so we're going to look at the maximum deformation for this entire structure here. Okay, and then for the deformation here, we have to choose which direction that we want to view the deformation. So let's choose the y-axis, just because if you remember from our static results, right? We had most of our deformation in this case in the y direction. So let's check our frequency response in that y direction. Okay, so once all that's done, let's go ahead and click solve. So that should solve everything here for us. Okay, I apologize. So it looks like in order to perform the frequency response, you actually need to apply the load separately. So we're not able to inherit the load from our static structural here, okay? So let's go ahead and right click on solution C6 and hit insert, okay? I'm sorry, we're gonna right click on harmonic analysis C5, and then we're gonna insert a force, okay? Now, if you wanted this to be really realistic, you could recreate all the loads that we have up here. But just so I can illustrate this to you, let me go ahead and just add a single force here, and we're gonna add it in the Y direction. Okay, so I'm gonna add in a force of 30,000 newtons in the positive Y direction. Okay, all right, so let's go ahead and solve this now. Oh, we may have to add a fixed support. We're gonna add a fixed support. Yeah, since it's not inheriting all the boundary conditions, we have to add our fixed support as well. Oh, we actually got something. Let's see. Okay. Actually, let me go ahead and add that fixed support here, just so that we can see. Oh, actually, I think it already inherited the fixed support. Okay, that's good. Okay, so you can see here that this is our frequency response graph. Okay. So you can see here that wherever the graph spikes is where we have resonance occurring. Okay, so we can see we have our first kind of tiny spike here at a frequency of about 324 hertz. Okay. And we have another more clear spike up here at around maybe around 540, 550. Okay. And so if you compare that to the resonant frequency that we found from before, right? So let's look at our modal analysis, right? So you can see here that we have, we have a resonance at about 326 hertz. So that makes sense. And we have another, resonance here at about 540. And so those correspond to, to the peaks that we have here. Okay. But remember, this frequency response here was for deformation in the Y direction. Okay. And so if you remember, right, each of these resonant modes here have deformations in a given direction, right? And so if we look at the resonance for the first mode, you can see that most of the deformation is actually in the Z direction. Okay. And so if you wanted to see more pronounced resonance, you would change your frequency response here to the Z direction instead of the Y direction. And so that's going to change the shape of your frequency response curve. Okay. Actually, let me do that really quick, just so we can see. See response, deformation, look at the flange, maximum. And let's look at the deformation in the Z direction. Okay, so let's take a look. Okay, so you can see that this changed the shape of our curve a little bit. So we have a little bit more of a pronounced, loading our resonance occurring here. And of course, if you change the direction of the force as well, that's also going to change your resonance. And so if we, change the forcing to be in the Z direction instead, so let's see what that looks like. Let's go ahead and solve this. All right, so you can see that once we change the force in the Z direction, we get much more pronounced, resonance here at our first resonant frequency, which is 324. Okay. All right, so one other thing I want to show you, right before you guys go, right, is the comparison of the static deformation versus the resin deformation, okay? So your frequency response graph at 0 hertz, this is the static response. So you can see here from the static result, we get a deformation of about 0.77 millimeters, okay? But when resonance occurs, you can see that our deformation here gets amplified to about 2.69 millimeters. So that's an increase of about 3.5 maybe. Okay. So you can see resonance, amplifies your deformations. So, if you look at any engineering system and you amplify your deformations by about 3.5, that's usually a bad thing. That's usually not something that you want to occur in your engineering system. Okay, so this is just meant to illustrate to you, how destructive resonance can be in these types of systems. Okay. All right, any questions on this? Okay, all right, so that's modal analysis and harmonic response, and so definitely a great candidate for your final projects. So I'll stick around for the next 5 minutes if you have questions on your project or the activity. But if not, thank you guys for coming this week. Hope you guys have a good weekend, and I will see you guys next week.
Right now, it was sketch.
Okay, looks really good. Yeah.
We already divvied up for
Oh, that's fine. That's when you do a lot of these complex. But yeah, that's because for a lot of these, even for the midterm probably a lot of people had to push it further. But yeah, that seems pretty reasonable.
Okay.
But yeah, this looks really good. How many is it again? 600? Yeah. I would probably go a little bit harder with the dynamics one.
I feel like it's
Just to try it first. Right. And then you can see how much that.
Yeah.
And then, with the dynamics one,
I mean, you're already going the dimensions of it.
How are you able to push it? Because I know this.
Well, I used to.
Over here. Oh, okay.
I did it here.
Oh, okay.
Yeah, I know I couldn't
Oh, yeah, yeah, I wouldn't, yeah, for dynamics, I wouldn't, yeah, I would use less.
Oh, yeah.
Maybe like 15. To 16,000.
Oh, okay.
Yeah,
Not as bad as I thought I.
Yeah, very well. Fine, there.
Okay.
yeah, maybe two.